So as we moved to the ONOVA, we started to talk about kind of the model of omnibus tests. So both multiple regression and ANOVA are often omnibus tests. Both of them can be situations where you could run them as not an omnibus test. And remember, all an omnibus test means is that there is an overall test of any of the differences in the data for statistical significance, which allows us to make the claim that the model of all of the various potential relationships is significant of 0.05 or lower, which allows us to then go in and start doing additional tests. Now, when would a multiple regression not be an omnibus test? When you have a single IV and a single DV and you're just simply running. In other words, it's not a multiple regression anymore. But you could use the multiple regression equation to conduct that test. Now, again, simplicity is best. Do a correlation or regression. Likewise, you could run an ANOVA on a single IV with 2 levels and a DV. But again, you should probably do that with a t-test. Go with a simpler test. So generally speaking, multiple regression and ANOVA are going to be omnibus tests. They're going to give us an overall test statistic that is looking at all of the relationships across all potential variables and asking, is there enough systematic differences across any relationships for us to claim that the overall test is significant? If it is significant, that releases us to start doing additional testing. That lets us go deeper in the onion and start asking the question of which relationships are significant and at what levels. Now, at its most simple level, an ANOVA is a categorical variable that has 3 or more levels, so 2 plus 2, and a single outcome. So if we find the omnibus test says, yes, there's differences somewhere, we still have a question. Where is the differences? Because we have an independent variable that's categorical with 3 levels. Now, if we get an omnibus test, the F is significant, we know that whatever category or condition or factor had the lowest mean is significantly different than the one that has the highest mean. What we don't know is the middle. What about that middle mean? And again, if our categorical variable had 4 levels or 5 levels, the only thing that we know without additional testing from the omnibus test is that the highest mean is different significantly from the lowest mean. To find out if there's other differences, we have to do post hoc tests. And we briefly talked about various ways to do that. And again, you might want to review them from last year. Tukey's HSD, honestly significant difference test, is the one most commonly used. However, there are some situations where we either need a more stringent test, Sheffey's, or a more liberal or open test, Dunnett's. We can also do plan comparisons, pre-planned t-tests. We only use those, though, if we're only interested in certain differences. In other words, if we had a categorical variable with 5 levels, but honestly all we care about are 1, 4, and 5, we don't necessarily then need to test 2 and 3. We could skip those and do pre-planned comparison t-test. The big thing with a priori means before we ever run the statistics. So we don't run the statistics and then go, well, it's pretty clear 3 and 4 aren't related to anything, so I don't want to test for those. That's not how a priori works. A priori means we already planned based on theory to only look at certain relationships. All things being equal, Tukey's HSD. Now remember again that if we have multiple IVs in an ANOVA, we're going to have a main effect for each IV, A, B, and honestly it can get as complex as you want, C, D, E, F, G for that matter, and any potential interactions between the two. So if on the most simplest level we have a 2 by 2 factorial ANOVA, so a 2 means a 2-level first IV, by 2 means a second IV with 2 levels, factorial means we have more than one IV, and in that case, what we're going to have is 3 actual effects beyond the omnibus test. We're going to have a main effect for A, a main effect for B, and an interaction effect. And each one of these is going to be looking at a different thing. Main effect for A is simply the effect of A over error. Main effect for B is simply the effect for B over error. And the interaction is the total effect minus the effect of A and effect of B. In other words, is there an effect that is beyond the main effects that needs to be accounted for? If there is, that means A and B are interacting with each other. And we kind of went over various ways to identify this, that main effects do not necessarily equate to interactions, and interactions do not necessarily equate to main effects. You can have a very strong interaction and no main effects. You can have two very strong main effects and no interaction. So they are different animals, and we are looking for them in different ways. And again, I would suggest that you go back to your notes and kind of review the ways to identify main effects and interactions with graphs and with mathematical tables like this one. Generally speaking, if we're talking about main effects, especially if we're looking at something like this, a table, what we're asking is the mean of the first factor, regardless of levels of the second factor, different from each other? In other words, are males different than females, ignoring what type of therapy they had? The main effect for therapy would be, is there a difference between scores in therapy? Cognitive behavioral therapy versus psychodynamic therapy, regardless of whether they're males or females. And finally, an interaction is likely present if we find that the trends going from box to box, kind of clockwise or counterclockwise, are different. In other words, when we look at males going across the two types of interventions, what is the difference, and what is the difference between females? If we're not finding an interaction, those differences should be about the same, +3 or +4 each. But in this case, there's a strong indication of some form of interaction. Males get better going from one therapy to the other. Women get much worse. And we also talked about how to identify this with graphs. And again, the general idea here is that when we're looking at this, we're basically trying to average the various different groups to look for main effects. So again, ignoring males and females and on both the average mean of psychodynamic versus CBT therapy, we can get an idea of what that difference is. And the difference, but the overall difference between the two lines is the main effect of whatever the lines represent. And finally, if those lines would cross, or would ever cross, there's a potential interaction. And again, we just kind of talked about how once we actually know that there's an interaction, we're not doing post hoc tests, we're doing simple main effects. So if we find that we have a significant main effect on an independent variable that is categorical with 3 or more levels, we need to do post hoc tests for each one of those significant main effects. For each interaction, we need to do simple main effect tests, basically comparing every box to all the other boxes to find out where are the significant differences within the interaction. And as a final note, when you find an interaction, the interaction is usually far more important than the main effects, because generally speaking, the interaction is telling you that the main effects themselves are not telling you the full picture. The only time, in fact, we'd ever really even talk about main effects in the presence of an interaction is if we did have specific hypotheses based on theory that focused on those main effects. Broadly speaking, if we have a significant main effect of gender, a significant main effect of therapy type, and an interaction between gender and intervention type, at that point, we wouldn't even talk about the main effects anymore, because it really isn't appropriate to say that females respond better to therapy than males, even though that's the main effect. It really wouldn't be appropriate to say that cognitive behavioral therapy is better than psychodynamic therapy, because that is the main effect. Because the reality is something more along the lines that potentially males respond differently to therapy than women. And depending on whether you're a male or female might guide what therapy you should use. And again, with ANOVA, we also still need to consider the size of the effect. And again, that's effect size. And again, we're normally going to use partial eta squared, which gives us, again, roughly, it's similar to R squared. It's telling us how much variance is being accounted for by that particular effect. And also recognize that much like with all the other statistical techniques we've talked about, ANOVA does have its assumptions. If it's a between subjects design, those assumptions include categorical IVs, single continuous DV, independence of scores from categorical level to categorical level, normal distribution of the DV, and homogeneity of variance of the DV across all your conditions. In a repeated subjects design, again, we have categorical IVs, we have continuous DVs. We lose the requirement for independence, but we gain the test for sporicity. We still need normal distribution, and we still need homogeneity of variance. And again, just as a recognition, anytime we run a statistical test, before we ever run the test, we need to test the assumptions. We need to ask the questions. Do we have the right variables for this test? Have I done the right methodology to allow for this test? And have I checked the distribution of my DVs to make sure they're normally distributed and I have homogeneity of variance in the case of between subjects, and whether I have sporicity, normal distribution, and homogeneity of variance in the case of repeated subjects. And remember that issues of sporicity exist for all effects that involve repeated measures with a K of more than 2 IVs. And the way we usually test this is Malachi's test. And again, if we find out that we do have a problem with homogeneity of difference or sporicity, what we're going to have to do is either do an adjustment. So we can basically do our homework and look at the 3 adjustments that SPS often gives us, or we can simply look at the multivariate option. So we can actually use multivariate tests in the case of sporicity being actually violated, and we'll talk about that more this semester. So once again, let's wrap up with whenever we're running any statistical test, in this case we're adding the complexity of an omnibus test, we're first going to check assumptions. We're going to eliminate outliers if it's appropriate. We're going to conduct mathematical transformations if it's required to get that DV distributions. We may even use adjusted statistics. We're then going to report the omnibus test results, the actual statistic and effect size in P. Then, if significant, we're going to examine within factor differences, the main effect differences with post hoc tests. And again, we're going to talk about effect sizes there as well. And finally, if we have interactions that are significant, we're going to conduct our simple main effects. And finally, we're going to report all significant differences using both means and standard deviations and put it into English. What do these differences actually mean?